Hey guys, my name is IBM and I'm still taking you through solved past paper questions. I'm taking you through magnetic fields and electromagnetic induction. These are past paper questions for physics 9702 from 201 to 2025. So this is going to be episode 26 or part 26. So this is part 26. Do not forget to get the document. You can write to me, leave a comment, and I'll be able to help you to find the document with the past paper questions, or you can find the documents on the website. A long straight vertical wire A carries a current in an upward direction. The wire passes through the center of a horizontal card as illustrated here. Okay, so the card is viewed from above. The card is shown from the figure. The card is shown from above in the figure 10.2. So here it is seen from above, which means the current is coming out of the page. That's why we see that dot there. Okay, so the current is coming out of the play of the card. On the figure, draw four lines to represent the magnetic field produced by the current carrying a wire. So we imagine gripping our wire in our right hand with the thumb pointing the direction of the current as illustrated by this image here. And the fingers fold in the direction of the magnetic field, and you notice that the fingers are folding the anti-clockwise direction. So we know that the magnetic field pattern around a current carrying wire are actually concentric circles. They're concentric circles, but their separation increases as you move away from the wire because the field strength weakens as you move away from the wire. And the strength of the field is represented by how close the field lines are to each other. So they have told us to draw four lines to represent the magnetic field. So I will draw concentric circles. I always encourage my students to use a compass to make these ones to be very neat. So concentric circles whose separation keeps increasing as you move away from the wire. I encourage students to use a compass to make them uniform. Okay, so those are the magnetic fields. Then the direction is anti-clockwise according to the right-hand grip rule that we have used here. So these are going to point in this direction here, anti-clockwise. Okay, two wires A and B are now placed through a card. The two wires are parallel and carrying currents in the same direction. So the current is in the same direction. Explain why a magnetic force is exerted on each wire. So because there is current in each wire sits, of course, current in a wire creates a magnetic field around it. And each wire therefore is going to be sitting in the magnetic field due to the other wire. And because the magnetic field is in the horizontal plane, yet the current is in the vertical plane, the magnetic field is perpendicular to the current, and by Fleming's left-hand rule, there is a force. Or each wire then therefore experiences a force due to the magnetic field created by the current in the other wire. So explain why a magnetic force is exerted on each wire. So we say the current in each wire creates a magnetic field around the wire. The current in each wire creates a magnetic field around the wire. The current in the magnetic field, and I want to make this to be one line. The current in each wire creates a magnetic field around the wire. And each wire sits in the magnetic field created by the other wire. So each wire sits in the magnetic field created by the other wire. And for each wire, like I say, the magnetic field is concentric circles in the horizontal plane, and if the current is in the vertical plane, that means the magnetic field and the current are perpendicular to each other. So for each wire, the current is perpendicular. The current is perpendicular to the magnetic field. Due to the other wire. For instance, the magnetic field around this wire spreads, but remember it is in the horizontal plane, and therefore the current in this wire here is perpendicular to the magnetic field in this wire here, which is in the horizontal plane, and the current is in the vertical plane. So the current is, this is at 90 degrees. If the field is a tangent in that direction, the current, and this is 90 degrees, the current is perpendicular to the magnetic field. So for each wire, the current is perpendicular to the magnetic field due to the other wire. So each wire experiences a force according to Fleming's left-hand rule. State the direction of the forces. Of course, the forces on each wire, the force on each wire is towards the other wire. Force on each wire is towards the other wire. I want us to note that whenever wires carry current in the same direction, the force is attractive. You could say the force is attractive. We have explained this, I think, in equation 4c in part 1. You can check in part 1. Whenever wires carry current in the same direction, the force is attractive, that is towards each other. If the currents were to be in opposite directions, the forces would be repulsive. For instance, here, using Fleming's left-hand rule, remember the current is in the horizontal plane, the field is in the horizontal plane B, and then the current is in the vertical plane and they are perpendicular to each other. So the first finger pointing the direction of the field represented by B, and the current in the vertical plane represented by I, the thumb will point towards the left. So the force on wire B due to the current in wire A, or due to the magnetic field caused by wire A, would be towards that direction. In a similar way, the force on wire A due due to the magnetic field created by wire B, would be towards that side if we use the same if we use the same Fleming's left-hand rule. If I draw a magnetic field pattern around wire B, which spreads up to the position of wire A, remember the field is going to be in that direction, which is actually anti-clockwise. At the point of wire B, wire A, it will be in this direction here. That is towards the bottom of this card. This is going to be the magnetic field, a tangent to the circular path, or I mean to the circular magnetic field line at the position of wire A. And if you use Fleming's left-hand rule here, with the field pointing that direction, remember these are perpendicular to each other, with the field pointing in this direction here, that is the first finger, and the second finger pointing the direction of the current, that is upwards, still the thumb is going to point towards the right hand side. So in a nutshell, what I'm saying is that whenever wires carry current in the same direction, the force is always attractive, and when the wires carry current in opposite directions, the force is repulsive. You can check question 4C in part 1 of these episodes. The current in the two wires the currents in the two wires are not equal. The currents are not equal. Explain whether the magnetic forces on the two wires are equal in magnitude. So whether the currents are equal or not, the magnetic forces are going to always be equal, because by Newton's third law, the forces will be equal but opposite. The force on wire B, because of the magnetic field caused by wire A, is equal but opposite the force on wire A because of the magnetic field caused by wire B. So by Newton's third law, of motion, the forces are equal but in opposite directions. Or we also mentioned that you can state this in by referring to the product of the currents. The force between two wires always depends on the product of the two currents in the two wires, so it's going to be the same in magnitude. Or you can say the force on each wire is proportional to the product of both currents. And so the forces are equal in magnitude. Because the force depends on the product of the two currents or both currents, it is going to be equal in magnitude. Define the Tesla. Earlier on we have defined the Tesla. We said if you look at the equation F equals to B sine of theta, where B is the magnetic field, we are going to define the Tesla when theta equals to 90 degrees, so that sine theta equals to 1, and B is going to be equal to F over I times L. So in other words, it means that 1 Tesla, which is the unit for B, is equal to 1 Newton per ampere per meter. So a unit of magnetic flux density of a field which is normal to a long straight conductor carrying a current of 1 ampere and causing a force of 1 Newton per meter of its length. So it's a unit of magnetic, flux, density of a field normal to a long straight conductor, normal to a long straight conductor or a long straight wire carrying a current of 1 ampere and causing a force of 1 Newton per meter of its length. A unit of magnetic flux density of a field normal to a long straight conductor carrying a current of 1 ampere and causing a force of 1 Newton per meter of its length. So it's force per ampere per, it's Newton per ampere per meter. A magnet produces a uniform magnetic field of flux density B in the space between its poles. A rigid copper wire carrying a current is balanced on a pivot. Part PQLM of the wire is between the poles of the magnet as illustrated in the figure. So this is the illustration here. PQLM is in the magnetic field. Of course, you and me know that the magnetic field lines originate from north and terminate to the south. Okay, the wire is balanced horizontally by means of a small weight W. The section of the wire between the poles of the magnet is shown in the figure. So they have showed us now the section of the wire which is in the magnet, between the poles of the magnet here. Do not forget the magnetic field lines originate from north to south. Explain why section QL of the wire gives rise to a moment about the pivot. So when you look at section QL is this one here. So let's assume, or they gave us the current was flowing like this. So in section QL, the current is flowing like this, like that. So the current is flowing like this, it is flowing like that, like that. So look at section QL. When you look at section QL and you apply Fleming's left-hand rule using this figure here, applying Fleming's left-hand rule, the current is in this direction here. That's why you're not seeing the second finger. But the field is from north to south. That's why we're seeing this finger pointing this direction here. The force on this section here is actually going to be downwards as indicated by that thumb. What does that mean? The force on this is downwards. So it means if we have a pivot somewhere there and there is a force on this side downwards and we have a pivot somewhere there, this is the force. The force on QL is in that direction there and we have a pivot. So what does that mean? This force has a perpendicular distance from the pivot, therefore it is going to cause a moment. Okay, so we shall say that section QL is perpendicular to the magnetic field. Is perpendicular to the magnetic field. So a current in wire QL gives rise to a vertical force. That is by Fleming's left-hand rule. As I've illustrated by Fleming's left hand, the force is in the vertical plane, which does not act through the pivot, or it has a perpendicular distance from the pivot, which does not act through the pivot. The force does not act through the pivot and thus causes a moment. Thus it causes a moment about the pivot. So a current in wire QL will give rise to a vertical force. So the force is going to be vertical by Fleming's left-hand rule. Therefore, and since this force does not act through the pivot, then it means it causes a moment. Okay. Then section PQ and LM of the wire do not affect the equilibrium of the wire. So when you look at section PQ, for section PQ the current is downwards. That's why you see the second finger is pointing downwards, but the direction of the field is still the same. When you try to use your left hand with the first finger pointing say towards the right hand side and the second finger pointing downwards, you'll see that the thumb is going to be pointing towards you if you are holding the paper in the vertical plane. If the paper is on a table, the thumb is going to be pointing towards the roof. And if you try the same with section LM, the field is towards the right hand side. If you make the current point upwards, that is if you are holding the paper in the vertical plane, that is upwards, the thumb is going to be pointing towards the paper. If your paper is on the table, make the first finger point to the right hand side and the second finger pointing towards the roof. The second finger pointing towards the top of the page. The thumb is going to be forced to point into the page. That means the force is going to be into the page. Now notice that FPQ and FLM are going to be in opposite directions. It is the same current flowing into the wire. Therefore, the force on PQ and LM is going to be the same if the length PQ and LM are the same in the magnetic field, but they are in opposite directions. So you can explain this by referring to the fact that they cancel out each other. And also you can think about them as acting in the horizontal plane. Therefore, they will not cause a moment. They don't have any perpendicular distance from the pivot. One, you can think about them as cancelling out each other. The forces on PQ and LM are horizontal and act through the same line. And because they are going to act through the same line, they are going to cancel out each other, as illustrated by these Fleming left hands here. Okay, so I'm going to simply say that the forces on PQ, the forces on PQ and LM are horizontal and act through the same line. The forces are equal in magnitude. The forces are equal in magnitude, but in opposite directions. And so cancel out. Okay, so the forces, one is going to be in the horizontal plane, but out of the page. The other one is in the horizontal plane and into the page. The two forces are going to act in the same line, therefore they are going to cancel out. They are equal in magnitude because the current is the same, and if length PQ is the same as length LM, then the forces are equal but opposite. Section QL of the wire has length 0.85 centimeters. The perpendicular distance of QL from the pivot is 5.6 centimeters. When the current in the wire is changed by 1.2 amperes, W is moved a distance of 2.6 centimeters along the wire in order to restore equilibrium. Okay, so we have to move W, or the weight, through a distance of 2.6 in order to cause or to restore equilibrium. The mass of W is 1.3 times 10 to the power of minus 4 kilograms. Show that the change in moment of W above the pivot is 3.3 times 10 to the power of minus 5 Newton meters. So change in moment is going to be equal to the force times the change in the perpendicular distance, because we have to change the distance, times the change in perpendicular distance, that is from the pivot. So to restore equilibrium. So this is going to be the force. The force is going to be actually the weight, which is going to be M times G, times the perpendicular change in perpendicular distance, which I'm going to call L, change in L. So the weight, the mass of the weight is going to be, or it's given as 1.3 times 10 to the power of minus 4, 9.81. Then times the change in length, the change in the perpendicular distance, which is 2.6 times 10 to the power of minus 2. So that is 1.3 exponent minus 4 times 9.81 times 2.6 exponent minus 2. So that is 3.31516 times 10 to the power of minus 5 Newton meters, which is approximately 3.3 times 10 to the power of minus 5 Newton meters. Okay. Use the information in Roman 1 to determine the magnetic flux density B between the poles of the magnet. So for equilibrium, the change in clockwise moment should be therefore equal to the change in anti-clockwise moment, because to restore equilibrium, there had to be a change in moment. And therefore, for equilibrium, the change in moment, which is the change in clockwise moment, should be equal to the change in anti-clockwise moment. So I will simply say the change in clockwise moment should be equal to the change in the anti-clockwise moment for equilibrium to be restored. So that means, of course, we know that the change in anti-clockwise moment is going to be caused by the force on this section here. The force on this section here is what disturbs equilibrium and the anti-clockwise direction. So by moving the weight further, we now bring in a clockwise moment to restore the anti-clockwise, or to balance the anti-clockwise moment. Therefore, we shall simply say that the change in the anti-clockwise moment should be equal to the change in the clockwise moment, and the change in the anti-clockwise moment is going to be equal to the change in the magnetic force times the perpendicular distance from the pivot. So change in anti-clockwise moment is equal to the change in magnetic force. Or is going to be equal to the magnetic force, not change in magnetic force. Is going to be equal to the magnetic force times perpendicular distance times perpendicular distance from the pivot. So the magnetic force is going to be given as Bill. This one is given as Bill. Okay. So the magnetic force which causes a moment acts on QL, whose length is, the length of QL was 0.85 centimeters. Therefore, because the change in clockwise moment was given by this one here, so I'll simply say that 3.3 times 10 to the power of minus 5 should be called the anticlockwise moment, which is going to be B, or B times, of course, the change in current, because they said when the current in the wire is changed by 1.2, so that is change, there will be a change in magnetic force, which is going to be delta I times the length L of the wire in the magnetic field, then times the perpendicular distance x. So this is the force, magnetic force times perpendicular distance x. So this is going to therefore mean that 3.3 times 10 to the power of minus 5 is going to be equal to B times the perpendicular distance, which is, change in current, which is 1.2. The length in the magnetic field is 0.85 centimeters, so that is times 10 to the power of minus 2. Then times the perpendicular distance from the pivot. The perpendicular distance of QL from the pivot is 5.6. So this is times 5.6 times 10 to the power of minus 2. So we are making B the subject. I will just simplify the right hand side first. 1.2 times 0.85 exponent minus 2, then times 5.6 exponent minus 2. Then on the left hand side I have 3.3 exponent minus 5 divided by the answer. So that is giving us 0.058. So B is 0.058 Teslas. 0.058 Teslas. Okay, let part 26 end there. See you in part 27. Until next time, bye bye.